Next up, we will talk about mechanical indicating instruments. So first up, most basic one we have is a switch. In this case, this is a precision switch or a micro switch. We'll call them pretty regularly. All we have is a spring right here and a movable contact along with a secondary contact. So what happens is as this plunger pushes down, the key with this spring loading is it takes a small amount of movement on the plunger, even down to like a millimeter or two, to be able to deflect this enough to break the secondary contact and open the switch. This is really useful because if we have basically on-off kind of installations, like say landing gear down locks, like we'll see in the next page, we can tell if that circuit is closed or open, which is going to tell us a lot about if a certain system is safe to use. So in this case, the down locks must be in place for the aircraft to be able to land and not have the landing gear fold up. So by using 3 micro switches in series, we can make sure that all 3 gear are down and locked, which shows up as a green happy light inside the cockpit, which the pilots can easily understand. If we get more advanced, we can take 3 in separate branches and we can feed it through an AND transistor to send off to, let's say, a ICAS system or something else to give a electronic view of the landing gear if they're safe to use or not. On the flip side, we could have 3 micro switches that indicate 3 different indicators for the landing gear. So we may know if 2 landing gear are down locked, but if we don't have a down and locked indication for the 3rd landing gear, we can differentiate instead of just having a light that says we're good to go or not. Pretty simple. They're very, very robust. They don't tend to break very often, but most commonly we can see issues with contamination or maybe even wear over time causing them not to work. So we do have to troubleshoot those on occasion. We're going to get a little more complex right now, but I don't want you to fear too much. We're going to talk about remote indicating systems using synchros. Synchros can be either direct current or alternating current powered. And the job they do is pretty simple. Basically, we have a transmitter right here, and we want whatever is happening at the transmitter to be indicated over at the indicator. Pretty straightforward. This is usually when a mechanical linkage would not be sufficient. Maybe the run is too long, it would weigh too much. There's a couple different options. But basically, all we have is battery power that gets sent into our rotor or wiper here in the middle of this ring. This whole unit right here in a DC system is going to function as a variable resistor. I'll say that again. This entire transmitter in a DC synchro system is basically a variable resistor with 3 phases that come off and go over to our indicator. Depending on how current flows through this coil, it'll change the amount of current that flows over to these magnetizing coils over here, changing the magnetic pole, which is in turn going to change which direction this indicator points based on the magnetism. Very, very simple system. As the slide points out, we might see this with something like cowl flaps. You might see it with a radiator door. You might see it with a oil cooler door or even traditional wing flaps. It really just depends. The more complex cousin of this is the Magnuson remote position indicating system. This is going to be fundamentally the same, except instead of using a variable resistor, we are using magnetic field to cut current. We can kind of get away with this because we have a permanent magnet in the middle as our rotor on the transmitter and on the indicator. It's basically the same setup on either side. And we're transmitting this in 400 hertz AC. You'll notice, though, that it's only 26 volt. It's not the typical 115 that we would see through an entire aircraft. So it's a much lower voltage. But the nice thing about this is it allows us to run indicators a long distance. So while a small aircraft, it may be worthwhile to use a DC Selson system because we don't have a long run to make. On the flip side, if we were using a indicator, I don't know, for like a rudder position sensor on a 747, that's a much longer run, and a DC system is not going to be practical just based on the length that needs to be covered. So as a result, we use an AC system for easier transmission. I'll try to keep this simple. The way this works is a permanent magnet is going to rotate according to the position of what's being measured. The magnetic field that projects from the north and south poles of that permanent magnet are going to cut the lines of current going around this soft iron core. That in turn is going to change the amount of current that's being transmitted in 3 phases over to our indicating Magnuson. Over on the indicating Magnuson, that is going to change the amount of current that flows through each section in between phases. Remember, when we have three phases, they share a neutral, so it's going to act as a parallel circuit. So it's going to vary the amount of current that flows through and magnetizes this ring, which is going to attract our permanent magnet here to point in one direction or another up in the cockpit. That is as simple as I can make it. It's a fairly simple system. As we get more complex, this is a AutoSyn remote position indicating system. And the thing that I really want to stand out on this is that it fundamentally works the same as what we see with the previous version, except instead of permanent magnets, we're using single phase AC to power an electromagnetic rotor. The stator windings are still going to be fundamentally the same. It's a Y design. We're transmitting AC in three phases from the transmitter over to our indicator, and it's going to change the amount of current flow through each phase, which as a result is going to change the amount of magnetic draw. But the rotor on both sides, it's a single circuit over here, is going to be energized by 400 hertz AC single phase. So just keep that burned into your brain. Next, we're going to talk about G-units. That wasn't funny. I enjoyed it though, and this is mostly here to entertain me, so there's that. Accelerometers measure G-units, and G-units are important because in some cases we can only pull so many. You have kind of a built-in G-unit as a person, because if the blood leaves your brain, then you black out or have what we call a G-lock, G-induced loss of consciousness. On the flip side, if you go the other direction, you pull too many negative G's and we can have a redout, which is arguably a whole lot worse than a blackout because we force way too much blood pressure into your brain, which tends to have negative effects. But anyway, neither here nor there. As we take a look at the accelerometer, this is a very simple device that uses a weight on a pulley that's going to deflect either way, depending if we're pulling positive or negative G's. Like most of the mechanical indicating systems we've seen, it's going to use a spring to oppose that power. So this spring right here that we see, this is our centering spring. That centering spring is going to make sure that we show 1G as our neutral position. Remember, 1G is what we all experience all the time. If we have twice the force of gravity in effect on us, that would be 2Gs, right? On the flip side, if we have negative Gs, if we go from 1G to 0G, that means we've opposed the force of gravity almost exactly, and we're experiencing weightlessness. If we go beyond that, now we're pulling negative G's, and we are going the opposite directions. Now we're experiencing the load of the Earth's gravity pull, but in reverse. So that 9.8 meters per squared acceleration constant, anyway, doesn't really matter. Back to the accelerometer, the way this device works is we have two needles that will deflect in either way for positive or negative. And we have our main pointer. The idea is we have one pointer that's going to hold its position for the maximum amount of G. So these auxiliary pointers will deflect and they'll stay there. This main pointer is going to be our active indication. So the main pointer will move back and forth. These auxiliary pointers will stay at their highest peak. So if we pull up to 3Gs, which is about what this is indicating, then that auxiliary pointer will stay there until we push our pointer reset shaft, and it'll allow these pawls right here to let go of the ratchets and let those slap back to their neutral position, because now they're being forced on by the centering spring. However, this main pointer right here, you can see it's running through the interior shaft that goes straight over to that centering spring. Whenever we were not actively under a sizable G load, it's going to be snapped right back to its neutral position. Again, you're going to open one of these up, but that's how it works. You may even see some aircraft that use a G counter in conjunction with an accelerometer to determine how many times an airframe has undergone certain G loadings, which can help us to track fatigue on the aircraft over a longer period of time. So that's what we have. Next, we're going to talk about stalls. Yes, stall equipment is considered a mechanical indicating type. And really, all of this comes down to the fact that while airspeed plays a component, it is not the only indicator of whether or not an aircraft is going to enter a stall. Because ultimately, as airflow enters the leading edge of our boundary layer here, it should smoothly divide at the front of the airfoil and go over and under the wing. However, as we start to slow down and as we start to increase our angle of attack, then we can get what we call a burble. So instead of a smooth division, we have a piling up of air pressure effectively at the leading edge of the wing, which actually starves the top of the wing for the air pressure that it needs. We lose our laminar flow, we lose our lift, and the aircraft falls out of the sky, which is not good. So our most basic form of this is a stall warning transmitter. So all we have is basically a little micro switch in the body with this little tab up at the front. As we start to get airflow that burbles, it's going to deflect that little tab upward, and we get a stall horn that goes off inside the cockpit. Pretty straightforward. On the other hand, there's simpler versions. They have little like vane types, but we're going to stick mostly with the electronic types here. What we're also going to take a look at is its more advanced cousin, the angle of attack indicator. These come in a few different forms. We may have a vane that sticks out on the side of the aircraft that's going to change with the direction of flow. What the angle of attack indicator tells us is the angle of the aircraft's longitudinal axis, so the one that runs from tail to nose, the angle of that longitudinal axis to the angle of the relative wind. So if you can picture this, right, our relative wind will be coming straight at the aircraft, but as the aircraft starts to pitch up further and further, that angle becomes greater and greater. Now that actually has a much larger component to do with stalls than airspeed necessarily does by itself. So this is really important. In a lot of cases, our angle of attack indicator may be hooked up to something like a stick shaker inside a commercial aircraft cockpit to warn the crew of an impending stall, or it may just be hooked up to an angle of attack indicator. That angle of attack indicator, in a lot of cases, is being fed through some pretty complex autopilot systems, which will help the aircraft to stay in a more safely operable envelope. But again, that kind of gets to a totally different side of what we're talking about. But for the device itself, you could see the vane type, or in this case, you'll see the airstream direction detector. All this does is we have slots right here that allow pressure to come in. And as that changes, the pressure flowing through those slots is going to change, and it's going to act on this paddle inside the paddle chamber. So instead of having an external vane, you can kind of picture it like we're transmitting the air pressure inside to use an internal vane to be able to change this. So this will wipe against a potentiometer, and it's going to send a signal up to the cockpit. Again, basic system, but it's important to know what it does. Usually when we're working with larger aircraft, right, we may have a couple different versions. A lot of times we have things referred to as bite tests, which are built-in test equipment to the computer systems on the aircraft. In other cases, we may get weird squawks, talking about like angle of attack sensor disagree. A lot of times we'll have multiple redundant angle of attack sensors to make sure that a failure of one does not cause the entire system to have a cascading failure. It's not to say that it hasn't happened, but again, we aren't going to dwell on that part. This is the instrument. This is how it works. This is what you'll need to work on. We'll see you for the next section.